Okay. Great. So I'd like to talk a little bit more about Statecharts at a conceptual level. So, here we have, with respect to a given condition, a set of states that are mutually exclusive and collectively exhaustive. They completely describe the weight categories, for example, associated with an agent. Normal and underweight, overweight and obese are completely described by those states. These are categories of things, and in those situations, a state chart is often a quite nice representation. Here, for a simple state chart, an agent is in one state at a time. There are more sophisticated state charts we'll be seeing later in the course, where an agent can be in more than one state at a time. You can have hierarchical state charts, where you could have a dysglycemic state, and inside of that, there's a diabetic, a pre-diabetic, and a diabetic state, for example, that are substates. Okay, and then there are these predefined transitions between states that are associated with certain semantics. The transitions between states occur instantaneously. You're not in the transition for some period of time. You go from one state chart to another. And I have some slides related to this. Okay, I wanted to talk about the specific types of transitions supported by any logic. We've seen some of them, but I think they merit further explanation. One is a timeout transition. We saw that early on as the default, and a timeout transition would be associated with a very specific time of transition. I will quickly illustrate to you. You don't have to follow along this, but a simple timeout state chart, if you wanted to see this. And I will go add an agent type. You could see how I do this. And go to there, and we're going to add an oval here, and I'll make it nice and smaller and put it up here. And then I'm going to go to main, add a population, and make it a population of size 100. Then I'm going to go to person, and I'm going to add a state chart. So build early, build often. I live by that rule as well. Next, I'm going to go add a state chart. Okay, to do this, I go down to here, and I'm going to add example state chart. And let's add in state 1 and state 2. Okay, state 1 and state 2. Okay, state 2. There we go. And we're going to make this be a timeout transition. You'll notice the timeout transition is denoted like that, and we'll make the reverse be timeout as well. This will be a very visual depiction of what's going on. We're going to make the appearance of this agent depend on whether they're in state 1 or state 2. So we're going to have their fill color be dynamic, and specifically it'll be example state chart is state active, and it'll be state 1. They're going to be red, otherwise green. Okay. So here we have this nice little state chart, or minus of the holiday seasons, and we're going to. Oh! I forgot the key thing. Oh man. Okay, go to main. Set the layout to be random. Right. This is like a reminder of what you got to do. There we go. Okay. See what's happening here with the timeout. It's like those cannon bombs of old. So they all transition at the same time. Why? There's no heterogeneity. It's a fixed timeout, ladies and gentlemen, associated with each person. It's a fixed timeout of 1. They go after precisely that time. It's precisely delineated time that they come in. Now, you can, and it will be fruitful to do so, set these timeouts to be drawn. If you want to draw it from a particular distribution, you can also use a timeout, but say draw it from a log normal distribution between with log mean 1 and log standard deviation of 1 and a minimum value of 0 here, and we could then run this, and here we'll see this decoupling that goes on, because what this is saying was when someone comes into here, it will actually draw the time at which they should leave from this distribution. So if you want to impose a certain specified distribution for their timing of leaving, you can do so with a timeout. It's not just for fixed times. You could draw it, the time at which they should leave from this time from a distribution, and impose your arbitrary, non-memoryless transition process. If you want to impose a beta distribution or draw it from a gamma or what have you, you can do so here. So timeout transitions are very useful if you want to have things happen after exactly some period of time. We saw that yesterday in our loss of immunity. Or if you wish to draw from a custom distribution, or from a distribution. AnyLogic does support custom empirical distributions, so you could define your own distribution. You could draw things from that if you want to. You want to draw values represented from empirical data. Okay, so timeouts are useful and are very flexible once you realize you could draw the value from a distribution. Be aware that what it means is when you come into that state, that value will be drawn from that distribution, okay? And it's specific to that person. It's not, to this particular, sorry, it's not to that person. It's when you particularly come into this particular instance. The next time they come into here, it may be a different value drawn from this distribution, okay? Okay, so that's fixed, timeouts. By contrast, a fixed rate transition, like we've been seeing in our model, of which our model had many, these fixed rates are associated with a memoryless process. It's exponentially distributed residence time within that state from which they're coming. So it's memoryless. You have the same chance of leaving per unit time, regardless of how long you've been in that state, right? And so when it needs to figure out what that is, it will simply draw the value from an exponential distribution with this as the parameter. So that's a memoryless process. Timeouts are memory full most emphatically, unless you, of course, happen to specify a value for them that's drawn from exponential distribution. You can have variable rate transitions. We saw that here. Just be aware. This has it changes at certain times. For example, when agent re-enters state. So this one had a variable rate, but it kind of woke up and recomputed when it was to leave whenever that rate changed, because that rate was set by changing these other states. So it kind of woke the agent up and said, hey, recompute your rates, and it recomputed it. We saw that quite visually at one point. Here, these rates, these variable rates are extremely powerful, but just be aware that you need them to be recomputed in a timely fashion. And if the rate is not always going to change at a time corresponding to changes of another state chart, you'll sometimes put in a self-transition. You'll see this in the example model I've given you, a self-transition from a state to itself. And that maybe bears some noting. In AnyLogic, this is a thing which I found amazing when I first saw it. Amazingly, I was just flabbergasted. But this transition is different than, the semantics of that are different than if it goes outside the agent. So if it actually, oh man, come on. Oh man, you can make me do that. Oh, come on. Oh, come on, you dumb thing. Okay, so let's try that again. So you can make a self-transition, and it's different if you have it go within a state like this, or if it actually leaves visually the state, so something like this, okay? This actually means it leaves the state and comes back in. If it's within the state, it's actually remaining in the state, it's just going off at a certain time. And there's a difference between the two. It only recomputes the rates leaving that state if you go out of the state like that, okay? So you should be aware that if you want it to kind of recompute this rate, if this rate depends on something which is changing over time, not related to sort of other transitions, in general, you need it to recompute it, and you'll want to use a transition which goes out and comes back in. You'll see an example of that in the model that I sent. You can also transition when a message is received. After lunch, we're going to be spending the balance of the afternoon working with messages and with networks and so on. And this is extremely useful. You can also do it based on a predicate, based on some condition. When a certain condition is reached, then you will have then the state will be triggered. And again, it will only check that condition at certain times by default. And those include, I'm almost certain, times when other state charts change. So just realize you may have to kind of wake it up and say, hey, smell the coffee, go check this condition, okay? And then finally, you can have a transition based on an arrival at a destination with mobility. And tomorrow we'll be examining mobile agents which move over the space. And here, we saw that some yesterday, but if you arrive at your destination, can be used to trigger a transition between states. Okay. A couple other things that are very useful. Often in empirically grounded models, particularly, we want a certain number of people to start in one state versus another. And there's very easy ways that you can do that within any logic. There's several ways. Probably the way I find most favorable would be, there we go. Would be most favorable would be to do something like this. And, fine, I'll just do it here. You can use a branch. And a branch transition allows you to sort of go in two or more directions based on certain conditions obtaining. So, for example, we could have the agent starting in this state. This indicates where they come in. And they could either go to non-diabetic state or diabetic state based on some condition. Okay. So, for example, we could have a parameter that specifies their sort of initial diabetic state. And we can do the same thing for weight. It can handle 3, 4, 5, any number of different things. So based on their initial diabetic state that's passed to us, we could either go to, so this would be initial non-diabetic transition, okay? And this might be the default. And then we'll have this one be initial diabetic transition. And this is based on a condition. What's the condition? The condition is initial diabetes state equals, and I'll just be sort of specific, so be consistent about it, so you don't have to get confused about when it's needed. You could test this sort of thing, okay? It says initial diabetes. I must have misspelled it. Okay, initial diabetes state cannot be. Oh, it's initial diabetic state. Okay, yeah. You notice that was my friend. My friend told me that this cannot be. So any logic is telling me, I don't know how this model works. I don't know what you mean by this model. And it's telling me this initial diabetes state can't be resolved. Double click on that, and I'm brought to this, and I want to make it renamed. I could have spared myself that grief if I had used the autocomplete, but I can also just diabetic, come on, initial diabetic state. Okay. Oh, come on. It got stuck. I think I have some key stuck on my machine that occasionally sticks. There it goes. Hey, no. Try this again. Okay. Oh man. Okay, you want me to type it on? Initial. It's a control key thing, I think. Oh man. Initial. Yeah, it's not listening to some key. Okay. Sorry, there's some key stuck here, which is preventing it from properly processing certain keystrokes. Initial diabetic state equals diabetic. That's what I want. And if we have this, person.diabetic, sorry, person.diabetic. If we have this, then we should be able to run this model and get it so that we parcel people out into these certain categories. So some people start diabetic, some people start non-diabetic. And that might be determined according to the population in which these people are embedded. Okay. So where do we specify the initial diabetic state? Where do we specify the parameter? Anyone? Sorry? In main, and specifically associated with the population, right? So I'm still having trouble with this, but I think maybe now it's been cleared. Okay, here we go. So it's associated with the population and its initial diabetic state here. So suppose we wanted 5% of the population to start diabetic and then 95% to start non-diabetic. How might we do that? Anyone? Trying to think what we've seen thus far. Suppose we wanted 95% to start non-diabetic and 5% diabetic. So yeah, so what we could do is, and I'll type it up here. So what we want to do is random true with 5% likelihood. So this will be true with 5% likelihood. Then we'll start in person dot non-diabetic, otherwise person dot diabetic. Okay. That's sort of the thing. So with the certain probability, we're going to start non-diabetic. Otherwise, we'll start diabetic. So 95% of the time. Other way. 95% of the time non-diabetic. Otherwise diabetic. That'd be a very grim situation. Otherwise. Here we can. Paste this in, and let's give it a try. Oh, look at that. Okay. Condition. Sorry, rookie mistake. It should be double equals. Okay, and yes, another rookie mistake. Sorry. There we go. So what we did is we implemented a transition, a branch transition here, where people come in and they're parceled up into either a default case where they're non-diabetic or a alternative case where they're diabetic. We go and we run the simulation, and some people now are going to begin already in a diabetic state. You could see what the initial diabetic state is over there, and you'll notice this is state 4. So they started diabetic. This person started diabetic. It's actually encoded as a number here. Okay, so this is a way in general in any logic to have people start in different states. So if you want to divide up a population so there's a prevalent set of individuals in each category, you can do so by implementing a parameter which you then pass, like initial diabetic state, you can pass it from the population in which they're embedded. Okay? No, I made this, it specifies, for generality, I made it so it just specifies the state, the particular state. This is sort of a identifier indicating whether it's a diabetic state that should start in or non-diabetic. And I did that because with a Boolean, we could handle two. That would be sufficient. A Boolean would be sufficient for this because it's dichotomous. But in general, if we have a state like that's of this sort, then we'd have to divide it up into three possible categories. Yeah? Yeah? Oh, it shouldn't be a double. It should be actually, technically it should be a short. An int would be fine. It's actually a value that's an integer, but it's a short integer. So technically, I should probably for greatest compatibility, I should make it a short, but an int will be fine. Thank you for pointing that out. Yeah. Okay. So that strategy will work for state charts with any number of different states. Any questions about that? Yeah. Yeah, I said it here. Yeah. So with a certain probability, we choose one versus choosing another. And if there were multiple states, yeah. Yeah, you could have a discrete distribution among them, and any logic supports custom distributions by which you could, from which you could draw what value you want them to have. There's a couple different ways you can do this. We have models where we'll read in from the database and sort of dictate how many people of each type to create and sort of explicitly create them. Another way would be to do it like this. And, ideally what you'd have is a draw from a multinomial distribution. So with a certain specified vector of probabilities, you'd have a certain specified vector of probabilities associated with a specified set of states, of state values, and you could use, there's Java libraries that offer multinomial distributions. I don't think multinomial is built into any logic at this point, but there's libraries out there on the web that are there are Java libraries that include multinomial distributions, and you could draw from a multinomial, and you would give it a vector of probabilities, something like it'd be something like new int something like this, 0.05, 0.95. I wouldn't do this because I'm just showing what it would look like, and then you could do new int. It would actually be ideally a short, but it doesn't really matter in this case. Person dot non-diabetic and person dot diabetic, something like this. But that's what in general you'd like to do, and there are libraries online that will do that for you. Okay. But this is a common need, and so I thought I'd just mention it. Okay. Hey, okay, you won't give it back to me. Fine, I'll put it in. Person dot non diabetic, otherwise person dot diabetic. Okay. Any other questions before we break for lunch here? Okay. So what have we seen? This morning, we've seen once again quite a lot. We've seen that we can encode. We started with a parameter. We introduced a parameter for main to set the population size. We saw that parameters are, like most any logic objects, they can be used, well, virtually anything that can be used in main can be used in an agent class and vice versa. Main is itself an agent of sorts. So we set a population size parameter, and that population size parameter, we set it to be an integer, and then we set the population size, the population itself, to depend on the value of that parameter for its population. We then went into new chart, and we saw that the value for that population parameter, that parameter specified in main, is specified where? What specifies the value of parameters in main? Simulation. The appropriate experiment. Yeah. In this case, it's called simulation. So those will specify the value. Great. And then we went to person, and we started adding a state chart. And we found we could add a state chart. We found that there are a variety of types of transitions. And we had first started with these rate transitions, but we implemented a message transition. We'll be looking at things like that this afternoon. So when we sort of say, hey, sort of through some exogenous influence often, make this happen, say an intervention, we could make them switch between states. And then we displayed the state color using this color variable so that when we went between states, we could change color and it would update accordingly. And we saw that allowed us to display in a visual way people's state and its evolution over time. We then implemented a historic value that kept track of history information on a given agent, and saw that could be displayed found at an individual level. And we then set it so that their size was contingent on that color, that history information. So this radius. We then went up to main, and we saw that within main we could specify statistics. For example, that kept track of totaled up the count of occurrences of overweight over the entire population, and we saw that there could be a statistic that would compute the fraction of the population that had a certain attribute. We then added in additional state charts to this person, and so we had a non-diabetic state and a diabetic state. Each state chart sort of kept track of a classification and dynamics associated with a certain type of concern. In this case, occurrence of diabetes. In this case, occurrence of weight and weight change. And we could add similar state charts in fairly modular ways to an agent over time, without dealing with a combinatorial explosion like we get in an aggregate model. We then went and further refined the situation, added texture to it by having the two state charts interact through a variable, this hazard rate, by which would mediate the timing of occurrence of diabetes in this other state chart. So someone's state within this weight state chart would then impact their progression in this other state chart. We finished up by looking at some ways in which we could divide up by different types of transitions, and ways in which we could divide up a person into different states using a branch. And a branch is not restricted for its use to when they come into the state chart. We will routinely have branches, for example, within a state chart going from one state to another. For example, if you're exposed to an idea or exposed to a pathogen, there's a certain chance it might stick, so to speak, that you'll get sick from it. You'll be influenced by the idea. And so we might use a branch transition to represent that. You're exposed, and then 95% of the time you stay within your original state, otherwise you progress to another state. So branch transitions are very useful for handling contingent sort of situations. And we further saw some discussion about the ways in which we use timeout transitions to capture arbitrary time in which you spend in a state. The final thing I just wanted to note is that these are the basics of state charts. We do have hierarchical state charts, which basically group together one or more states that have general features into a single overall state. This is actually not a particularly good one. This is from a built-in AnyLogic model, but I would highlight one of the models that I provided to you. Specifically, there's a model that's, and I'm trying to think which it is. Right. There's one called the, and it's called Beifeng-Ren model. And this is a model which is fairly articulated, and I'm going to be discussing it potentially later as a little case study. But this is a model that's notable for several reasons. Notably, it's a hybrid model combining agent-based modeling, system dynamics, and discrete event simulation in a single model. And you'll notice that within this model, we have states which are hierarchical in nature. So, for example, these are dialysis modalities, and then within it we have peritoneal and hemodialysis. And one of the big advantages of doing this is that if you have transitions that conceptually would go from any state within dialysis, for example, to death, anyone within either the dialysis modalities is subject to death, you just have a single transition from the hierarchical state chart. And similarly for receiving transplant. Someone who's either peritoneal or hemodialysis can receive a transplant. So we don't have to create transitions from each of these substates. Instead, we could just create one transition from the enclosing state. Similarly, this transplant area, we delineate these three states because the chance of graft failure and the cost involved is very different for each, but there's only one transition to death. We don't have to create separate transitions from every state and every state for graft failure. Instead, we can just have one transition for all of those. So hierarchical state charts are useful. You can associate actions with the overall state that would otherwise need to be replicated for each of the substates, and you could just group those in a single place. Okay, so that's that particular use of hierarchical state charts. Okay, I think I'll leave it at that. We can break for lunch, and we'll reconvene. Is that right? Or
yeah. So lunch is right outside. It's a box, and it has what their sandwiches, and it tells you what it is on top. And then we have that room next door that I'll open up available, so you can sit down and not in front of your computer.
Great. Thanks very much.
Reconvene at 1 o'clock.
1 o'clock is.
I don't know. I mean, we had.
Yeah.
Or 12:45.
Yeah.
We had 45 minutes, but we.
Okay.
We should. But it's already 12:07.
Yes.
How long do you want?
Let's say. Are people comfortable eating for 12:45? Yeah. Okay. Seem good with that? Okay. We'll do 12:45. Yeah. Okay. Stay on track.
Yeah. Where are we actually?
We were ahead this morning, and I spent a little bit more time on state charts, partly reflecting that. So, we were ahead. Now we're a little bit behind. Okay, so we're going to be doing receiving messages now. Yeah. So, yeah. So we're sort of in this area in here. Yeah.
I have to go and lead a webinar this afternoon.
Yes.
Which is really unfortunate timing, so I'm nervous about. How disastrous is this going to be to miss and try to come back in tomorrow?
Not hugely disastrous, but I would, if possible, I'd try to watch the video that comes out of it.
Okay.
But if you can't, we could get Priya-Sri to sit next to you and
that might be good. Help me get caught up real quick.
Precisely. Yeah. Are you gonna leave and come back, or are you gonna leave and not be able to come back today?
Well, I have to facilitate the webinar,
right.
And I'm afraid of doing that from a computer that's not mine.
Mm-hmm.
And I'm an hour away, so I feel like
you can't really realistically come back. Yeah.
It's really unfortunate, and then yeah.
Yeah. No, I understand. So, what I'd say is, if possible, maybe try to review it, but otherwise, maybe we could get Priyastree to walk you through it.
Maybe I'll come in a little early tomorrow
Yeah?
in case you all get
Yeah.
here early.
Yeah.
I want you to meet really quickly. I want you to meet Keaton.
Hi,
who is
Keaton.
At
Nice to meet
Renzi
you.
as well.
Oh, okay.
I'm trying to set up a dinner on Friday evening
Okay.
with anyone from Renzi and Maria, but I think it's so Steve Stahl, Keaton, and Sid.
Okay.
Yeah, and Ashok and others from Renzi who haven't been able to come to this.
Sure.
So just
That's great.
either I'm going to shoot for either Friday evening or Saturday morning.
Okay.
Heads up that you are.
Okay. Okay.
Yeah.
That's great.
Yeah.
So we scheduled things on Saturday, so my flight doesn't leave till I think 4 or something.
That's great.
So I'm flying to San Diego, but this will allow me to spend the bulk of the day here.
That's great.
Yeah.
Great.
Yeah.
Unfortunately, I'm going
This afternoon.
tomorrow and
Oh, okay.
Thursday because I have to be at an NSF meeting.
I see.
So that's what.
Okay.
But Keaton will be coming and going. Yeah, and Keaton, like Steve, is on with staff or faculty. I don't know what your title is.
Okay.
At Renzi, and so really stable
Great.
people
Great.
that I want to get
Yeah.
doing this
I work
well.
primarily in healthcare sector. Right?
Sure.
Leading
Okay.
the decision, I'm leading the decision support initiative.
Uh-huh.
Currently in healthcare sector, how do you take large amount of population data and
Right.
model it to a
Terrific. Okay.
fitting the perfect thing in terms of simulating the condition because it's hard to get real world patient data.
Indeed.
Right?
Yeah.
Then how do you kind of take this approach and
Mm.
kind of circumvent that thing?
I understand. Yeah.
So just wanted to kind of
Mm.
get insight from you.
Mm.
How do you kind of have you applied this
Oh, yeah.
healthcare? Sorry, I didn't read more on the background and other things.
So, oh yeah, I mean we've used this on a large numbers of different projects. We've done some of them related to health care. Most of our work is upstream, so it's issues that have to do with population health and public health. But a number of our models, including the one you just glimpsed, and another sort of involving patient flow and emergency wait times, for example, are very solidly linked in with healthcare issues.
I think that would be perfect.
Yeah.
To kind of see how you could kind of turn this around and show it in the application.
Sure. We had a TA from so I just came from delivering a boot camp at UCLA.
Okay.
And and at UCLA, well, maybe I'll bring this in there. At UCLA, I had a TA who's actually been the primary one driving forward the work with the stuff for our Ministry of Health on patient wait times and patient flow. But it's sort of a system-wide perspective on patient flow that incorporates of Yep, I think I'm in good shape. Thanks so much.
Water, coffee?
Yeah, I got some water here. I've got a secret bottle down here for in case I need it.
I think everybody's thrilled.
Oh,
Awesome.
wonderful. Well, thank you so much. Okay, sure. As you need. Yes, thank you. Pardon me. I'm just gonna. Oh, okay, good. It looks like the audio kicked in. Okay, great. There you go. Yeah, I'll look forward to that. Thank you, Keaton. Testing. Okay. Great. Test. Okay. Okay, good. Good. Okay. Okay. Great.